Greetings everyone. Me, Ankita Saini, with my team member are going to present this video presentation on neuromorphic computing. Now, I give a brief introduction on this topic. Neuro, which is something related to brain. Neuromorphic computing refers to the design and development of computing system inspired by the structure of human brain. Over past decade, many companies and organizations have been working on neuromorphic computing, including IBM, owner of True North chips. The core concepts are neurons and synapses. In the brains, neurons communicate by electrical signals, while synapses are the junctions that transmit signal between neurons. Neuromorphic systems replicate this structure with artificial neurons and synaptic connections. Spike based computing. Unlike traditional computing that processes information in binary ones and zeros, neuromorphic systems use spike brief electrical pulses. This approach allows for energy efficient computation. Learning and adaptability. Neuromorphic systems can learn and adapt to new information through synaptic plasticity. Now, the next, parallel processing. Neuromorphic systems can process multiple tasks simultaneously, similar to parallel processing that occur in brain neural network.
Hi everyone, myself Vansh Rana. I am going to explain the materials used in neuromorphic computing. In this, we will discuss about basic materials of neuromorphic. First one is neuromorphic chips, memory registers, complementary metal oxide semiconductor, software frameworks. First material is neuromorphic chips. These chips simulate how biological neurons communicate using spiking neural networks, where data is transmitted as discrete electrical pulses similar to the brain. First one is Intel Lohi. This neuromorphic research chip developed by Intel features SNNS for real-time learning and pattern recognition, sports, on-chip learning and adaptive behavior. Second one is IBM True North. Developed by IBM, this chip contains 1 million neurons and 256 synapses, extremely low power consumption, designed for sensory processing tasks such as vision and sound recognition. Third one is spiking neural network architecture, created by the University of Manchester, capable of simulating large-scale brain models with millions of neurons. Highly parallel architecture using thousands of ARM cores. Now, second material is memory registers. It acts like biological synapses, storing and processing data in the same location. It can remember the amount of current that passed through, mimicking memory retention. It enables energy efficient and fast learning in neuromorphic systems. It is useful for building non-volatile memory in neuromorphic circuits. Third material is complementary metal oxide semiconductor, that stands for CMOS. Traditional transistor technology used in standard processors. In neuromorphic computing, CMOS is adapted to build artificial neurons and synapses, integrate neuromorphic systems with conventional silicon chips, provide a bridge between biological models and digital circuits. Fourth material is neuromorphic software frameworks. To run and simulate spiking neural networks, several specialized software platforms have been developed. First one is NEST, that stands for Neural Simulation Tool, a simulator for large-scale spiking neural networks designed for neuroscientific research and computational modeling, can simulate millions of neurons and billions of synapses. Second one is Nango, a high-level framework for building and simulating neuromorphic models, sports, cognitive architectures, learning algorithms, and integration with neuromorphic hardware. User-friendly with Python integration and good for prototyping. Third one is Brain, a Python-based simulator for SNNS, prioritizes simplicity and flexibility for research and experimentation, well suited for small to medium scale brain-like models.
Hello everyone, myself Amandeep Singh and I will explain the methods used in neuromorphic computing, the core techniques that make this technology so brain-like and efficient. So firstly we talk about event-driven processing. Unlike traditional systems that are always running, neuromorphic system only processes information when it's actually needed. Just like how our brain responds to specific signals, that helps in saving a lot of energy. And the second method is real-time learning and adaptation. These systems can learn on their own without needing huge training data sets. They use techniques like spike timing dependent plasticity, which helps the system adjust and improve with experience without requiring labeled data. And the last type is hardware testing and simulation. The hardware testing and simulation neuromorphic chips are tested in real environments like for image recognition or robotics. These chips are also used in edge AI where quick and energy efficient decision making is needed, for example in drones or smart sensors. So these methods helps neuromorphic computing work more like the human brain, being smart, fast and energy efficient. Thank you.
Hello everyone, I am Ojas Dharma and I am going to explain the future scope of neuromorphic computing. This technology is inspired by how the human brain works and it has the power to completely change how the computer thinks, learn and process information. Why it is important? Traditional computer processes data step by step, but neuromorphic system can handle many tasks at same time just like our brain. This makes them much faster and more energy efficient. In the future, this will be very useful in areas like artificial intelligence, machine learning and real-time decision making, especially where speed and low power are important. Future application. Let's talk about some future application. In self-driving cars, neuromorphic chips can process data from sensor instant, helping the car react faster to sudden changes. In healthcare, brain-like chips could be used in devices that detect pattern in heartbeats or brain signal, improving patient care. In smartphones and wearables, these chips can allow real-time learning, gesture control and even on devices voice processing without needing internet all the time. In robotics, neuromorphic system can help robots learn from their surrounding and adapt new situations just like humans. In space missions, where the power is limited, these chips can be used for intelligence data processing without needing big system. Advancement in research. Tech companies like Intel, IBM and Qualcomm are already working on neuromorphic chips like Intel Lohi, which can simulate millions of neurons and synapses. Universities and research labs are also exploring spiking neural network which use brain-inspired signal instead of regular digital bits. This system can learn faster and forget unnecessary data just like we do. Career and research opportunities. In upcoming areas, neuromorphic computing will create many opportunities for researchers, engineers and students in fields like AI, neuroscience, hardware design and brain-computer interfaces. It is an exciting area for innovation.
Hello everyone, myself Atul Bhardwaj. I am going to explain the challenges of neuromorphic computing. So the challenges in advancing neuromorphic computing are scalability, hardware limitations and standardization. So the first one is scalability. One of the primary goals of neuromorphic computing is to replicate the massive parallelism of the human brain, which contains approximately 86 billion neurons and over 100 trillion synapses. Scaling artificial systems to approach this level of complexity is extremely difficult. This occurs due to interconnect complexity. As the number of neurons and synapses increases, the connection between them grow exponentially, leading to increased data traffic, latency and energy consumption. Power, heat and heat management. Scaling up the system requires more power, which generate heat affecting both performance and lifespan of the hardware. Maintaining speed and efficiency. More neurons can slow down the system unless managed efficiently with advanced architectures and algorithms. Second one is hardware limitations. Neuromorphic computing relies on specialized hardware that mimics the biological neurons and synapses. However, most current hardware technologies based on CMOS processes, which is known as complementary metal oxide semiconductor processes. These are not ideally suited for this. This occurs due to complex architecture requirement. Neuromorphic systems often require 3D integration, non-volatile memory, and analog computing elements, which are not yet in mainstream in manufacturing. Device variability. Neuromorphic chips often depend on memristors or other emerging devices which suffer from reliability and uniformity issues. Material limitations. Materials used in conventional hardware may not support the bio-inspired behavior needed for long-term memory and adaptive learning. Third one is standardization. Unlike trading computing, which has well-established standards for processors, memory, and software interfaces, neuromorphic computing lacks unified frameworks for design, development, and evaluation. This occurs due to lack of benchmarks. There is no agreed upon set of tasks or metrics to compare neuromorphic system fairly. Software and toolchain inconsistency. Different platforms use proprietary or experimentally tools, making cross-platforms development difficult. Interoperability issues. Without standards, integrating neuromorphic components into existing systems or comparing them to traditional AI accelerator becomes problematic. Thank you.
So, very warm dusk currently present. As my friend explained you about the neuromorphic computing, so I would like to just conclude this topic. And neuromorphic computing is just like a human brain. It's more modern and it makes processing more fast. To understand neuromorphic system, it's like AI working on the behalf of our brain with a combination of modern technologies and our brain system. How neurons work, how it sends signal to the brain, it just artificially works in neuromorphic computing. Unlike traditional computers that follow step-by-step instruction, the system can process many things at once in neuromorphic systems and make the faster and more efficient processing of the signals and data. They use very little powers, which is great for a device like robots, smartphones, AI, medical tools, and self-driving cars. And AI makes it more easier. The system works using spikes in neuromorphic, just like a brain. Sends signals to the brain and uses artificial neurons and synapses to learn and make decisions. It includes hardware like Intel, IBM, True North, and software like Nest, etc. Systems are available for the softwares and which simulate how brain works. Method like spiking neural networks, event driven processing, and real thing like allow machines to adapt on their own just like humans. In future, this technology can revolutionize AI, robots, edge computing, and other smart applications. With time, neuromorphic is getting involved more and more and trying to be more advanced, whereas it may be working like sometimes like a brain to take more data and give more efficient outputs to the input to give the better and efficient response with time and with more accuracy. Yes, there are some challenges like making it more scalable and setting global standards, but researchers are working still to overcome these challenges, and with time in next I think 10 to 15 years it will be all over the world on global scale. And with this I would like to conclude, and I would like to give a special thanks to our Dr. Ankush Kapoor sir, who have given us guidance and encouragement to do this project. His valuable time made it more easier to understand neuromorphic and futuristic topic of this neuromorphic system. Thank you.